Hi, I'm Mary Brady, and this is my Lab 2, Motion of a Falling Object. So the purpose of this lab is to predict and observe motion using drag force and the force of gravity. The models and fundamental principles used are Newton's second law, which is net force is equal to mass times acceleration. Drag force opposes motion of a falling object, and gravity pulls an object to the Earth's center. The result of my lab was that the object accelerated to the ground, meaning the net force was not zero. Drag force had no effect in my scenario. The main physics ideas are the velocity update formula, position update formula, and drag force. I also used gravity on the Earth, which is negative mg, and gravity and drag forces act on the falling object, affecting the object's velocity. So assuming only gravity is acting on the ball in the first computational model, and we assume only gravity and drag force is acting in the second computational model in the experiment. Using Newton's second law, if the object is not traveling at a constant velocity, the net force is greater than zero. And if the object is traveling at a non-constant speed downward, the force due to gravity is larger than the drag force. So the system is the eraser, and the surroundings are everything around it. The initial conditions are it dropped from a meter above the ground. It was dropped from rest, so initial velocity was 0, and the mass is 0.009 kilograms. Here's my tracker video. You can see from the position versus time graph, this is not linear, so the velocity was non-constant. And here's my first computational model where we only take into account the force of gravity. And you can kind of see with position versus time, it is the same. It is not constant, but it has a steeper slope. And model 2 is where we account for drag and gravity. So in FNet, I added gravity and drag force. But my B was 0 because of my calculations and trying to match my computational model data to my observed data. So it ended up being the same as my first model. So these are actually the same graphs because of that. But you can see the predicted model had a steeper slope than my observed model. And this is probably because drag force is acting in the observed or the experimental data. It was just too small for me to account for when I was doing my lab or doing my models. So you can see drag force is happening because it's not accelerating as fast. So some sources of error, my drag force was pretty small because the object was aerodynamic and fell a very short distance. So it was very hard to calculate the coefficient. And human error, I probably messed up when I was clicking my point mass in tracker. So what if the object was thrown downward instead of dropped from rest? It would have a greater initial velocity. So using the velocity update formula, it would have a greater final velocity because of that. But the velocity versus time graph would have the same slope because gravity and drag force would still be acting on it. So examine the velocity versus time predicted by your models with and without drag. So which model predicts a terminal velocity? So since both of mine were the same, I'm just using one velocity versus time graph. You can see this is a linear slope, but it is a non-constant velocity. So I don't see a terminal velocity because there is not a point in this graph where the slope is equal to 0. And the slope would be 0 in a scenario like terminal velocity where the drag force would be the same as the gravity force.